Here's an Olympic Model 447 transistor radio from 1956. Just a big AM radio that actually looks like a old tube lunchbox style portable. Okay, now, the burning question. What does a small electronics manufacturer in the mid-50s do when they want to get on the transistor radio bandwagon? You know, the first transistor radios came out in late 54, so 56 was still kind of early in the game, but everybody was wanting to get on that transistor radio bandwagon. So what does one do when they wish to get on that bandwagon? Well, I'll show you. What you do is you take your leftover tube portables, modify them for transistors, mount the 4 transistors in the existing tube sockets on the whole tube chassis, and solder them in place. Which is exactly what Olympic did here, as you can see. They actually made a tube portable radio that looked just like this, using the same chassis. And when they decided to jump on the transistor bandwagon, they just had their engineers modify all the leftover tube portables to operate on transistors. And this set still has the original, probably not the original, but period correct 9-volt batteries. This set uses 2 9-volt batteries in parallel for greater battery life. Obviously these batteries are dead, and I'll have to make up some sort of battery pack to operate this radio. And speaking of operation, I have no idea the operational status of this set. So let's take it down to the shop and connect the power supply to it and see what happens. Okay, we're connected to the DC power supply, set to 9 volts. Let's turn it on and see if we get any action at all. And it's totally dead. No static, no nothing. So this one's going to have to undergo some repair. And you can see that even the case of this radio has the opening for a power cord to come out, which would have been used for the tube type version of this set. So yeah, they literally took a tube set and modified it for transistors and said, here's our first transistor radio. And the chassis is easy enough to remove. Just remove 2 screws and it slides out. Now you can get a better look at the top side of the chassis. Here's the underside of the chassis. I see 4 electrolytic capacitors. Everything else looks like ceramic disc. And 1 electrolytic on the top side of the chassis. That's a strange looking output transistor there. Here's the schematic to the radio. Just a 4 transistor set. First transistor is the mixer. Second transistor is IF amplifier. Then we have our detector diode, then the audio driver stage, which is transformer coupled to the audio output stage. And just for fun, I printed out the schematic on the tube version of this set. There are some vast differences, but I really won't go into those now. One of these days I'm going to try to obtain the tube version of this radio, and then we'll do an in-depth comparison between the two. Okay, we've determined that there's no audio coming out of this set, except for a minor bit of crackle when I touch the power supply to the positive terminal on the battery connector. And I think I'm going to use the signal tracer method to troubleshoot this set to see where the dead stage is. And basically what this is just a high gain audio amplifier with a crystal diode installed in the test probe here. And this instrument is capable of demodulating an RF signal as well as amplifying audio signals. And if a stage is working, then the results will be heard from the speaker here. Okay, we're looking at the final output stage on the schematic diagram, and I think the first place I'm going to check with the signal tracer is the base of the audio output transistor and see what we get. Okay, that hum you hear is just normal. Now going to touch the probe to the base of the transistor, and we hear static. Now, pardon me while I put the camera down and tune across the dial to see if we're getting the reception.
Get only 40% seek treatment. The condition causes a sudden urge to urinate. As you grow older, the chances of experiencing overactive bladder increase. OAB can affect daily life, causing distress or sleep.
Well, the volume control is working.
President of Women in Government Foundation. Women in Government in a day.
Okay, so what that tells us is everything from the front end all the way up to the base of the audio output transformer the audio output transistor is at least working well enough to pass a signal. So we need to concentrate our efforts on this final output stage, and I bet you that output transistor is probably our culprit. Okay, now we'll check some voltages at the output transistor. Checking the collector. We have -9 volts, that's good. Checking the base. We have -1.4. Checking the emitter, we have 0. Well, since we have 9 volts on the collector, that tells us that the primary of the audio output transformer is good. In fact, when I place my meter leads across the primary, I get a click from the speaker, so that tells us that the transformer and speaker are both good. Get about 1 volt on the base, which I would expect to see something there. I'd also expect to see a little bit of voltage on the emitter, which I don't see. Now, I've already tested these resistors, and they're okay, so looks like this transistor is probably the culprit. Well, it looks like this transistor is the culprit. We have an open emitter-base junction, and we have our meter on the diode scale, our negative lead on the base, the positive lead on emitter, and since this is a PNP transistor, we should be getting a reading. We're not. So that means this transistor is open. And just to prove my point, I'll reverse the leads. And nothing. Now let's check between base and collector. Check that junction. Positive on base, negative on collector, nothing. Let's reverse the leads. We should get a reading. Negative on base, positive on the collector terminal. We get a reading, so that junction is okay. Between collector and emitter, we should get infinite reading, which we do. Now we'll reverse the leads, and we should still get infinite reading. And we get infinite reading. So we have an open, this base to emitter junction is open. And this is a germanium transistor, so we'll have to look up this original part number in the NTE book and some other resources and see if we can find a suitable substitute. If not, we may have to experiment with some silicon devices, and we may have to change the value of these resistors to get the bias right. And according to NTE, the CK751 cross-references to an NTE 102, which I think is a pretty common germanium transistor. And the 102 is a PNP germanium driver and output transistor. Now, the burning question is, will the local parts house that's getting to be more worthless every day actually have this part? Well, the miracle of miracles happened today. The parts house actually had one of these. They actually had 3 of them in stock. That's really something else. So, let's install this and see if it works. Okay, we have it temporarily installed. Of course, it sounds like we still have more noisy transistors, probably the driver transistor.
You need to hear. Your argument's not holding any water.
livingassistance.com. Your ancestors. They're for free this week. That's right. Go to tryancestry.com.
Okay, let's make this mounting more permanent.
Monday only, and you'll have 100%.
And then we'll work on this hissing problem.
Million birth, marriage, and...
Here's the old transistor, and they have it soldered to the heat sink. Now, I'm not too keen on soldering this new transistor to the heat sink, so hopefully I can just clip it in there. And given the low power that this audio amp is, I really don't think it's going to get that hot anyway.
In this industry.
Okay, there we go.
Now, when
that
you
should
say
work
insurance
just fine.
broker, are you going to work for a particular company?
And now we need to work on this hiss problem.
Of different companies.
Okay, thinking back, we had the noise on the base of the audio output transistor when we were making those first tests, when we found this transistor to be bad. And we have the noise with the volume control all the way turned down, which leads me to believe the problem is in this driver stage, which is based around a 2N132 transistor. So once again, we're going to use the signal tracer, and we'll check at the collector first, which I anticipate hearing noise through the signal tracer. And then we'll go back over here to the base where I anticipate hearing little to no noise. First, I'm going to check at the base of the driver transistor, and what I'm looking for is white noise, or interference, or whatever you choose to call it. I really am not looking for a radio station right now, so let's see what's at the base of the driver transistor.
All you need to get started at one great price of $35. That's 65% off. Now, we got a ton of other items in the offer.
Okay, no white noise at the signal tracer. Why do I keep calling it a signal generator? Okay, so no garbage here at the base. Let's move to the collector and see what we get. Plenty noise, plenty garbage coming out. My number one suspect, a noisy germanium transistor. Maybe I should have bought the other NTE 102 that they had at the parts house. Now, just for the heck of it, I'm going to test at the output of the detector diode.
If that's the way the deal went down. Now, if you don't own 100% of the house, that wouldn't be true, but that's if you owned 100%, that's what would happen.
That's clear as a bell, except for the hum out of our signal tracer.
And you talk about what the probate taxes are in the probate.
So that pretty much confirms that our mixer and IF stage and detector stage is in good operating order. And obviously our final output stage is okay. So it has to be this driver stage. Okay, I dug around and found a transistor out of a junk Magnavox stereo chassis.
Chance with the Islamists, Barry. He sat down one day and held their hands and took a deep breath and said,
and look at there, no static.
What did he just say? Was that a code? What was going on? You're right, I'm not. In the name of God, to what God has written in His Word.
Okay, that'll about do it for part one. In part two, we'll touch up the alignment and do anything else that we might can do to help improve this radio's performance. Okay, there you go. Thanks for watching, and part two will be up shortly. Okay, back on the Olympic 447 transistor radio from '56. You might recall in the last video the radio was totally dead. We got it playing by replacing the audio output transistor, and then we still had a lot of noise in the audio, which was caused by a noisy driver transistor. And radio does pretty good on local stations, but I'm going to do everything I can to get the best performance possible out of this set. Right now I'm going to check these electrolytic capacitors. This capacitor here is 100 microfarad. That's our emitter bypass cap for the audio output transistor. And it's reading 218 microfarad, and you usually want a capacitor test real high on a modern capacitance meter like this. That usually means leakage, high ESR. So we'll probably go ahead and replace that capacitor. Well, that's strange. It just went down in value and then jumped back up. Wonder what that. This one's a 50 microfarad, clocking in at 94 microfarad. Another 50, checking in at 82. Checking the same 100 microfarad cap on the old capacitor tester, reading about a little over 200, well, probably closer to 300 microfarad. Now I'll raise our power factor knob and see if our eye opens anymore, and it does not, so ESR is not a problem. Now we'll check for leakage on the 20 volt scale. Of course, this is a 6 volt cap, so we might just blow it up here. Yeah. Here's a new 100 microfarad 63 volt that test. It looks like about 100 microfarad on here. That's good. Now our leakage test, light goes on, then goes off. That's what it's supposed to do. Okay, I've replaced all 6, 1, 2, 3, 4, 5, 6 of the electrolytic capacitors.
When you order, the CEO of this great company is going to contact you directly and ask you, hey, what can we do to...
And I can already tell it sounds better and has more volume.
Free shipping, you get free expert advice. Blinds.com decorate.
This mayor's Christians need each other's prayers. The
And it also appears to be more sensitive.
John Hayes. Next, our final round.
Turn it all the way up and see if we can get the... Well, there's WYLS very faintly, hard to get station. Which is not too bad considering it's a 4-transistor set. Now, a few capacitors, I had to get a little unprofessional to install them because the leads on the new capacitors are not nearly as long as the old leads, so I had to splice onto the existing leads. And here's the underside of the chassis showing what was done. And there's a resistor here that I accidentally cut thinking it was a capacitor lead. And I just very carefully laid the resistor back over the terminal and was able to, well, let's just say we heavily tack soldered it back in place. I get real upset at myself when I do stuff like that, but these packed up chassis where they cramp a bunch of stuff in a tight space, that kind of thing can happen. Okay, the next order of business is to touch up the alignment, although I really don't think it's that bad out of whack. And the first order of business is to give the receiver and the signal generator the customary 15-minute warm-up time so everything will stabilize. And while that's taking place, I'm going to go sit on the swing and take a break for a little while. And then I'll come back and do this. Okay, we have our signal generator connected and set to 455 kC. The IF frequency, in this case, they want you to hook the ground of the signal generator to the chassis through a 0.1 capacitor, as well as the hot side to the tuning condenser, also through a 0.1 capacitor. And as usual, we keep our signal generator output as low as possible for a usable reading. We don't want that. And then we adjust as per the instructions here. First, we're adjusting the IF transformers. And we're adjusting L4, L3, and L2 in that order. And L4 is the output IF. There's only one winding there, and then we adjust the secondary of the input IF and then the primary. And I can't do this and hold the camera too, so I'll be adjusting this bottom slug of the second IF transformer for peak output, and then we'll move to the first IF transformer. Okay, they wore off a little bit, and that's about as good as I can get the IF line. Now they want you to loosely couple, as in radiate a signal from the generator into the radio. Set the knob in the radio and the signal generator to 1600 kC, and adjust C2, the oscillator trimmer, on the tuning capacitor for maximum output. Yeah, this is how I radiate a signal into the radio. Just loosely wrap the hot lead of the generator around the antenna. And I have adjusted the oscillator trimmer, this bottom trimmer here, for approximately 1600 on the dial. That's what determines your dial accuracy. Now they want you to adjust the generator and the radio to 1400 kC and adjust C1, this top trimmer on the tuning capacitor, for maximum output. Okay, and that adjustment was out of alignment. And since we have a station at 1390, 1400 was a little bit too close, so I just used 1350 as our test frequency. And last, they want you to set the signal generator to 600 kilocycles. Set the knob to approximately the same position. Rock the variable capacitor back and forth while adjusting L1, the oscillator coil, for maximum output. Okay, that's done. We'll now unplug the signal generator, disconnect everything, and check the radio's performance. Probably the station in town with the best music, but the worst signal. Go figure.
Trying to make the splash with Cochran and...
Okay, well that's pretty good. Let's put it back in the case now. And there we go. And one thing about these radios, you usually have to rotate the cabinet for best reception due to the directional nature of the antenna.
Turns trash into treasure. But the beat. In the South at the time, including ultra-conservative on the radio right now.
All right, 25 now till the top of the hour.
In 910, I seem to have a problem with it squealing on several radios, but okay, after dark, we'll come down here and do a nighttime check and see how sensitive this is.
Comes to mind from South.
Okay, and checking all of the capacitors that came out of the radio, the main culprit was this one right here. 6 microfarad capacitor in the AVC circuit. It's basically dried out and is non-existent. The rest of these capacitors read around double their rated value on the modern digital capacitance meter here, and showed leakage on the other capacitor tester. And there's the 6 microfarad capacitor right here in the AVC line. I didn't have a 6, so I used a 10, and it seems to work just as well. A couple of 50 microfarad capacitors that I replaced, I didn't have those. So I used 68 microfarad. I wasn't about to use my high voltage 47 microfarad caps in this application, even though it would have still worked. I just felt like that was a waste. Just for kicks, let's see what kind of voltage is in these old batteries. This one has 0.8 volts in it, and you can see it's dropping the longer the meter stays connected. And this second battery has 1.2 volts and dropping. So yeah, I thought that'd be fun just to see what 50-year-old batteries would still have in them. They're supposed to be 9-volt batteries. And obviously I'm going to have to build a battery pack for this radio.
And of course, in addition to that, our Medical Minute with WMER, CNN's very own.
And there you go, the 1956 Olympic all-transistor radio. Back in good operating condition again, and should be ready to go for another, hopefully, almost 60 years. Unless the other two germanium transistors decide to crap out on us.